Happy snow day number 3. Alright, so let's check out yesterday's lesson. I'm just going to do a quick video on finishing it up because we had course selections yesterday. So today we're going to be looking at the rest of solving quadratics, and I will be posting a video lesson on the next day, day 4, which is applications, which you will need for tomorrow's in-class assignment. I understand that it's also a buyout tomorrow, so if you're there in class, you'll do the assignment. If you're not, well, then you won't. That's kind of how I'm going to look at it with all of these delays and interruptions that have been happening. So here we go, solving quadratics. So today or yesterday was day 3. We looked at 2 distinct, 2 equal, and 2 complex conjugate real roots. Here we have 2 eyeballs, so 2 distinct real roots. We can see they're real, even if they're fractions, they're real. Their decimals are real numbers. Here we have 2 equal real roots. There's 2 of them that are kind of like on top of each other. They're identical, right? So 2 equal real roots. And then here we have 2 complex conjugate roots, and it's kind of like up in the sky. And we saw that yesterday when we have something under the square root sign. If we did what we call the quadratic equation and we got something that's negative and we get that I value, that means we're getting 2 complex conjugate roots. So that's when we're getting that I value. So maybe make like a star there. If we're getting like a square root of a negative number that's underneath our square root sign when we're doing the quadratic formula. So square root of a negative number is going to give us those 2 complex conjugate roots. Alright, we talked about the zero property, how a times b is equal to 0, therefore a is equal to 0, b equals 0. We solved for the nature of the roots. That's just like state the nature of roots. That means just like, is it 2 distinct, 2 equal, or 2 real roots? So we solved by factoring first, so it's already been factored for us, so we're just looking at the 2 different factors and making them equal to 0. Here we can see that there's 2 places, we get 2 values, so this is 2 distinct real roots that are happening, right? They're not at negative 3 and 1 are not identical, and there's no I, so yeah, it's 2 distinct real roots. And we can see that they're going in 2 different places. We also even found that when we add them together and divide them by 2, we get the line, like, okay, so those are the eyeballs, the negative 3 and 1, and then we get the line of symmetry, right? So it's right between the 2, so you add them up and divide them by 2, and then, so you get like your line of symmetry, and then from there, you plug whatever the line of symmetry is into the original equation, and you get your y value. So that would be like your chin. So once you find this line, you could plug it in and then get the y value. So here we can see it's also a minimum because the a value in front is positive. It's already in factored form for us, and then we use the zero property. So we've done both of these here. We've even stated the nature of the roots. Factor first, bring everything to one side first, make it look like a trinomial, and then from there factor it. Okay. Then once you get your 2 factors, it tells you if they're 2 equal, 2 distinct, or 2 complex conjugate roots. Alright, and then here we saw that this one's a perfect square trinomial. Anytime we get a perfect square trinomial, we're always going to get the 2 equal real roots. So we get that binomial squared. Those are 2 equal real roots. Yeah, they're 2 distinct. Like they're not distinct, right? Because they are identical, but they're not complex. So there's no I happening. All right, just give you a hint. If you can't factor it, it's most likely going to be complex, right? If you can factor it, then you know you're going to be getting 2 distinct or 2 equal real roots, because you can factor a perfect square trinomial and not have to do like the hint that we kind of did here, where you square root the first, square root the last, and then take the middle sign. Just make sure you're doing the little proof here, like square root of 9 is 3, square root of 4 is 2, and 3 times 2 times 2 gives you 12. So that means this is a perfect square trinomial. If this wasn't 12, like if it was negative 11, this is not a perfect square trinomial, right? So it's showing here that like square root of 9 is 3, square root of 4 is 2, and if we take 3 times 2 and we multiply it by this number 2, and we get 12, which we do, we know it's a perfect square trinomial. If it wasn't, then we couldn't do this helpful trick of answering it. Similar to what we do in completing the square, right? All right, that's exactly what we do in completing the square. So next, if you can't factor it, use quadratic formula. So put it into a trinomial, and I went over here that even if we don't have the quadratic term in front, the coefficient in front of the quadratic term is still a. Okay, so even if it looks like 8m plus 3m squared plus b is not, like 8 is not a. The a is always in front of the quadratic term. And then the b is always in front of what we call the linear term, or the term with the degree 1. And then c is always the constant term. All right, so we've got a, b, and c. We plug it into the quadratic formula. You should know this off by heart. We even had like a couple of singers sing for it in our class. So if you don't know it, you've got to know it. So make sure you know it. It will be on the assignment. It will definitely be on the test that is next Thursday, March 9th. All right, so we plug them in, and then here we can see that we get a negative value underneath. So the easiest way to do this is to figure out what's underneath the square root sign first. And this is what we call the discriminant. So calculate this first, get the value, and then from there, simplify. Okay, so from there we get negative 32, and we found that negative 32 is 16 times 2 times negative 1, which gives us 4i2, square root 2. And then the negative 8 and over 6 and the 4 over 6, we can split those into two different fractions, and then from there we get two complex conjugate roots. And why are they complex? Because we have the I. And why are they conjugate? Because they're just a plus and a minus. So that means there's one of them with the plus and one of them with the minus. Not the minus in front of like the b value or the negative 4 here. Those negative 4s stay the same, but the plus or minus comes from right here in front of the square root sign. That's just showing that one of them is positive and one of them is negative. All right, so this is where we left off here. So if it looks like something like this, you need to simplify and then use the quadratic formula. Okay, so let's go ahead and do this one. All right, maybe press pause and tell me exactly what the quadratic formula is, and then you can press play and see if you got it right. So press pause and try it out. All right, if you got negative b plus or minus square root of b squared, subtract 4ac all over 2a, you're doing a great job. We don't have the line like that, right? The line is not underneath the equal sign, it's not underneath the x like that. That's not what's going on here. It's all under 2a. Yeah, so it's not, our line is not only under here, it's the negative b plus or minus square root of b squared minus 4ac all over 2a. So even the negative b plus or minus all the 2a. All right, so let's input b is negative 9. So if it put negative 9 in here, we get positive 9. Those two negatives give us a positive b squared here, so it still is a negative 9, but we're going to square it. What's that going to become, positive or negative? Divided by 2 times 1. All right, so we've got x is equal to 9 plus or minus. Well, this gives us a positive 81. Negative 9 times negative 9 is 81 minus, what's that, 8 divided by 2. All right, so we get 9 plus or minus the square root of 81 minus 8. That gives us 72 divided by 2. All right, and now let's use our calculator and check and see what factors of 72 so we can reduce this. There, change it to 73, not 72. And I don't think there is anything. So yeah, we're just going to leave it. You try like 73 divided by, like 72 would be a lot nicer, but like 73 divided by, like try 9 and 4, and like all kind of your, any square rootable number going in 73. It doesn't seem like it, so we're just going to leave it as is. And so here we have x is equal to 9 plus the square root of 73 over 2 and 9 minus the square root of 73 over 2. All right, so 9 plus the square root of 73 over 2, and x equals 9 minus the square root of 73 over 2. And then what do we have here? Are they complex? Are they equal or are they distinct? Well, these are two distinct real roots. If you put them in your calculator, you'll get some decimals. These are what we call the exact values, and then if you actually calculated it, like 9 plus the square root of 73 all divided by 2 gives us 8.8, and 9 minus the square root of 73 all divided by 2 gives us 0.2. Right? Not beautiful to graph, but they are two distinct real roots. All right, we got the last question to go. All right, for this question, I just wrote over here because I was running out of a little bit of room. But a great hint here. So a great hint here is to not work with fractions. So how can we get rid of fractions? Well, there's this magic trick that we can do. All we do is find the biggest denominator or biggest common denominator and multiply everything by that. So literally we are going to just multiply this all by 8, and then it's going to eliminate the 4, and I'll get rid of the 8 here, and it will get an 8 here. So every single coefficient is going to get multiplied by 8. All right, and this is going to give us the exact same equation. It's just going to look a little different because it's going to be multiples of 8 instead. All right, so 8 times a quarter is 2x squared plus 8x is equal to, and we're going to multiply this by 8, negative 1 times 8 divided by 8 gives us negative 1. Now this is the exact same equation. If you don't believe me, I'm going to go graph it right now and show you. So here we are. We can see that when I click on it, these both equations are identical. Right. So now this is a lot easier to work with. Let's bring the negative 1 over the other side. And let's put it in the quadratic equation, a, b, and c. So we've got x is equal to negative 8 plus or minus the square root of a squared subtract 4 times 2 times 1 all divided by 2 squared. And this gives us negative 8 plus or minus 56. All right, 56 can reduce, and we get 2 in square root of 14. And then these can reduce. This and this, we're both going to reduce to, well, negative 8 divided by 4 is negative 2. And then 2 over 4 gives us the square root of 14 over 2. So we have negative 2 plus the square root of 14 divided by 2, and x is equal to negative 2 minus the square root of 14 over 2, meaning that we have two distinct real roots. There's nothing that's negative under the square root sign, so that means we have a positive result showing that they're two distinct real roots. All right, that's it.